Shrees. Today's video is on enthalpy diagrams.
So let's have a look at enthalpy diagrams. These diagrams show you the enthalpy and potential energy of the system on the left axis, and on the bottom there the reaction progress. You can see in this endothermic reaction that delta H is positive, and later the products have more enthalpy and stored energy than the reactants. Here's the activation energy for the forward reaction, and if you look over here you can see the activation energy for the reverse reaction. Notice that delta H for the forward and reverse reactions are the same with an opposite sense. And there's also this other interesting feature, and that is the forward activation energy is equal to the reverse one plus delta H. That's the conservation of energy law working for you yet again. This is a one-step reaction. Let's have a look at a diagram for a multi-step reaction. Here again, the enthalpy potential energy on the left, reaction progress down on the bottom. This one will be exothermic. In this multi-step reaction, you can see two peaks. Here's the first one, and that's the activation energy to do the first step. Here's the second one, the activation energy for the second step. Down here, of course, you can see between the products and reactants, again, delta H, the overall enthalpy change for the reaction. Also notice, over here, we have the activation energy for the reverse reaction. So what is activation energy? Just the amount of kinetic energy that needs to be available or added to particles to get them over that highest peak on the enthalpy or potential energy curve. So how about catalysis then? What does a catalyst do except decrease the activation energy and lower that highest peak on the potential energy graph? It provides an alternate mechanism. It's not directional in the sense it has to work both forward and reverse in the same way. Remember the conservation of energy law again. They can work on the surface, providing a location, or maybe it can be a chemical catalyst that provides a more reactive compound, or possibly it could act to hold the molecules into a more favorable geometry. It may also reduce electron repulsions. And let's have a look at what a catalyzed enthalpy diagram might look like. So here's a uncatalyzed forward exothermic reaction with a very high activation energy. There's the uncatalyzed one. And down here in the dotted lines, you'll see the catalyzed version of the same thing. Notice the activation energy for the catalyzed one is much less, and that there are at least two peaks here. Remember, you had to add a step, at least one, to get the catalyst in and back out again. Here you can see delta H is unchanged for the reaction. Here's an example of a catalyzed mechanism. This is ethine and hydrogen combining to form ethane. In the first step, the ethine combines with platinum. That's acting as a catalyst, is shown above the area to make these complex here, this intermediate PtC2H2. That gets consumed in the second step to make PtC2H4, and the last step gets combined with hydrogen again. You see these are intermediates. There's the second intermediate there in green, and you can see how they're produced and then later used up in a subsequent step. The platinum, on the other hand, is introduced and then regurgitated or regenerated later. You can imagine the reaction spitting the catalyst back out at the end. We show that catalyst that's first introduced and later comes out at the end above the arrow. Here's another example. This is an oxygen and chloride compound with iodide, making an oxygen and iodide compound with chloride. You can catalyze this one with water. So let's look at the reaction steps here. In the first step, the chloride oxygen compound gets attached with water, makes that ClOH compound, which in the second step gets attached to iodide and so on. OH minus is clearly an intermediate, produced and then used up. ClOH, again an intermediate, produced and used up. IOH, another intermediate, produced and used up. You can see water there acting like a catalyst, introduced and later regenerated. So the overall reaction is this Cl minus and I minus, making IO minus and the chloride ion. And we show that being catalyzed by water by showing water above the reaction arrow in this way. Okay, here's our last example for catalysis and mechanism. So in this reaction, we have this nitrogen compound with acetate ion, acetic acid, and then another version of that nitrogen compound at the end. Look what happens in these three steps here. Let me finish writing them down, and then we can discuss what happens in each step. So overall, we just see these acetate ion, that's clearly a catalyst, introduced and then regenerated. Acetic acid is an intermediate, produced and then consumed. This nitrogen compound is another intermediate, produced and later consumed. And so is the hydroxide, produced and later consumed. So overall, the reaction is this nitrogen compound coming apart, making dinitrogen oxide and water. again catalyzed by the acetate ion. Okay, notice this reaction takes several steps to do when catalyzed, and it's quite a bit more complex a mechanism than just a simple decomposition might be. However, even though the mechanism is more complex, it is a lower energy mechanism nevertheless. Okay, so the opposite of a catalyst, what is that? Something called an inhibitor. And of course, if you put an inhibitor and a catalyst both together, you might actually mess up the mechanism of the reaction so much it doesn't even proceed at all. So an inhibitor is used to slow down a reaction. It's kind of the opposite of a catalyst. Here's a summary. Enthalpy diagrams, they show the potential energy enthalpy of the system on the left, progress on the right, reactants on the left, products on the right. You can see in there delta H for the system. You can see the activation energy for the forward and the reverse reactions. And you can see the multiple steps. Of course, you can show them in this way, perhaps an exothermic one, an endothermic one, and so on. Each peak for each step. Catalysis, quick review of that, provides an alternate lower activation energy mechanism. You can add some complexity, but reduce the energy needs. The catalyst can work on the surface or as a chemical catalyst and so on. There's many interesting ways catalysts can work, and there's at least a few things there for you to discover more about in a later course. Also, they're not directional, so the forward and reverse rates are both increased by that reduced activation energy requirement from the catalyst. So that's about it for enthalpy diagrams and catalysis, at least for now. Thanks so much, and see you soon. So have a look at the next 2 videos in this playlist for more on the topic, and stay tuned for our next lesson in Chemistry 12, Lesson 7, Introduction to Chemical Equilibrium.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!